Hey everyone, welcome to another Explainer. Today we're going to bring some serious energy to conquering an absolute legend in the world of computer science and technical coding interviews for sure. We're talking about the maximum subarray problem. Now, if you're gearing up for software engineering interviews or, if you just genuinely love elegant problem solving, you've absolutely crossed paths with this one. It's a classic test. It checks how well you can take a piece of code from a slow, kind of clunky beginning all the way to an incredibly sleek, high-speed finish using Kadane's algorithm. So get ready, get focused, and let's decode this whole shebang together. Okay, let's dive right into this. Here's our roadmap for today. First, we'll define the problem itself. Second, we're moving from a brute force approach to a better one. Third, the star of the show, Kadane's optimal solution. And finally, we'll wrap up by handling empty subarrays and tracking those tricky indices. Let's get to it.
All right, kicking things off with Section 1, the maximum subarray problem.
So before we even think about writing a single line of code, we really need to completely understand the prompt, right? The problem is asking us to find the subarray that gives us the absolute maximum possible sum. But there's a critical and honestly super frequently confused distinction here that traps a lot of candidates. A subarray is a contiguous, continuous part of the array. So if you have the elements -1 and -2 sitting right next to each other, boom, that's a subarray. But if you pick a few elements, skip one, and then pick, say, a 5 later down the line, well, you've just created a subsequence. In a high-pressure interview, mixing up subarray and subsequence is basically a fatal trap. Just remember, for our problem today, the elements literally have to be side by side, perfectly continuous.
Moving right along to Section 2, brute force to better. Now, imagine you're in the hot seat. You rarely want to just jump straight to the ultimate answer, You really want to show the interviewer your analytical progression. So the most obvious initial approach is the brute force method. Honestly, this involves some pretty chaotic heavy lifting. We're talking 3 nested loops to physically generate every single possible subarray, calculate the sum completely from scratch every single time, and then track the maximum. But wow, that takes a massive amount of time. You definitely want to pivot quickly and pitch the better approach, which thankfully drops us down to just 2 nested loops. So how exactly do we achieve that upgrade? Well, it's actually by observing a pretty simple mathematical truth. Think about it. If you already know the sum of a subarray, let's say the first 3 elements, you absolutely do not need a third loop to calculate the sum of the first 4 elements from scratch. No way. You just take the previous sum you remembered and simply add that 4th element to your running total. By stopping those redundant calculations and just building on the previous sum, you cut the time complexity down significantly. But, of course, in a top-tier interview, better is rarely good enough. Which brings us to Section 3, Kadane's optimal solution. All right, this is where the tension peaks. Your interviewer leans in and asks, so, can you optimize this further? Can you do it in a single linear pass? Boom, it's time to unveil the masterpiece. Kadane's algorithm is actually built on a philosophy that honestly doubles as surprisingly good life advice. Do not carry any negatives into your future. Think about that for a second. If you're keeping a running sum of a continuous sequence, and that sum drops below 0, it has officially become a liability. A negative sum is literally only going to drag down whatever number comes next. Even if the next number is a massive positive value, adding negative baggage to it is just going to make it smaller. So Kadane simply tells us, drop it. Now, what's really interesting about this slide is how we can elegantly distill that philosophy into just 3 simple steps of logic. Step 1, you iterate through the array and add the current element to your running sum. Step 2, you check if this new running sum is greater than your all-time maximum. If it is, awesome, update your maximum. And step 3, here's the magic condition. If your running sum drops below 0, you immediately reset it to 0 before moving to the next element. You're basically saying, okay, this subarray is a lost cause. Let's just start a brand new one starting at the next index. Let's actually look at a concrete example from our source material that resulted in the maximum sum of 7. Imagine a slice of your array is 4, -1, -2, 1, 5. Okay, so when you hit the 4, your running sum is 4. Then you add the -1, your sum drops to 3. Add the -2, drops to 1. But here is the absolute genius of Kadane's. Even though we hit negative numbers, our running sum of 1 is still positive. It's still adding value. Because we held on to it, we carry that 1 forward to the next elements, the 1 and the 5, giving us a grand total of 7. If we had just panicked and dropped the subarray at the very first negative number, we'd only get a max sum of 6. The key takeaway? We only drop the running sum when it falls below 0.
And this brilliantly illustrates the massive payoff of Kadane's logic. Just look at the leap. We went from a clunky brute force time complexity of big O of n cubed down to the better approach of big O of n squared. But with Kadane's optimal approach, because we never look backward and we literally only maintain a running sum, our time complexity plummets to a single linear pass, big O of n. And the best part, it does all of this while maintaining a perfectly constant space complexity of big O of 1 purely because we're only storing a couple of variables to track our sums. It is, without a doubt, peak algorithmic efficiency.
All right, let's move to section 4, handling empty subarrays. Now, we all know an interview is never just about the happy path, right? We need to shift gears to a specific edge case that technical interviewers absolutely love to throw at you to test your thoroughness. I actually want to pose this exact question directly to you right now. What if every single number in your input array is negative? Say it's -4, -2, -3, -1. If you just run standard Kadanes, your max is going to end up being the smallest negative number, which is -1. But is that actually what the interviewer wants?
Well, it depends heavily on the strict rules of the specific problem variation you're given. In the source material we're studying today, there's a very explicit rule. You are allowed to consider an empty subarray. Think about it. If picking literally any element drags your score into the negatives, the absolute best move you can make is to pick nothing at all. And an empty subarray has a sum of exactly 0. So as a final safety check in your code, if your all-time maximum is still less than 0 at the very end, you simply return 0. Always clarify this edge case with your interviewer.
Finally, section 5, tracking subarray indices. So, you've provided the optimal linear solution. You've handled the edge cases like a pro. Now comes the inevitable follow-up question. Great, you found the maximum sum of 7. But can you print the actual subarray that gave you that sum? So the crucial point here is figuring out how to track our boundaries without adding another loop. And the logic is beautifully simple. We just introduce an answer start and answer end variable. Remember how Kadanes resets the running sum to 0 whenever it goes negative? Well, that exact moment of resetting to 0 is literally the birth of a brand new subarray. So whenever the sum is 0, we mark our current index as a temporary start. As we iterate, if our running sum suddenly beats the all-time maximum, we lock those variables in. Our answer start becomes that temporary start we marked, and our answer end becomes our current iteration index. It captures the boundaries perfectly, and yep, it still runs in big O of n time.
So we've gone from a sluggish, nested loop nightmare to a super elegant linear time solution that tracks indices seamlessly. But honestly, the lessons of Kadane's algorithm go way beyond just one interview question. As you continue your coding journey, I really want to leave you with this thought. How can the concept of dropping negative baggage optimize your approach to other algorithmic challenges? Where else in your algorithms are you carrying forward dead weight that you could simply reset to 0? Keep that mental model sharp, apply it to your future problems, and I guarantee you'll start seeing optimal solutions everywhere. Thanks so much for hanging out with me on this explainer. Keep learning, keep coding, and I'll catch you in the next one.